Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A young Foley Thomas, barely a fledgling mathematician, found himself wrestling with a problem that seemed to defy all known methods. He was attempting to model the intricate oscillations of a newly designed high-frequency antenna, a crucial component in the nascent field of wireless communication. The existing mathematical tools, while adequate for simpler scenarios, proved utterly inadequate to capture the nuanced, complex behavior of the electromagnetic waves. This frustration, this profound sense of the limitations of existing mathematical frameworks, would become a catalyst for his remarkable contributions. This essay will explore the profound impact of Foley Thomas's work, charting a course through the intricate landscape of complex analysis and its profound implications for physics and engineering. We will examine his groundbreaking methods for tackling complex functions, revealing the remarkable ingenuity and profound insights that shaped his contributions. We will delve into the historical context of his work, tracing the evolution of mathematical thought and the pressing scientific problems that spurred his innovative approach. This exploration will highlight the enduring relevance of his early work to modern mathematical and scientific practices, demonstrating the foundational nature of his contributions. The early 20th century witnessed a burgeoning interest in understanding the intricacies of wave phenomena. Electromagnetism, a newly discovered force, was challenging physicists and engineers to develop accurate models of its behavior. The propagation of radio waves, the transmission of electrical signals through space, demanded mathematical tools capable of capturing the complex interplay of variables. Existing mathematical approaches, often limited to real number systems, were proving insufficient to model the multifaceted nature of these phenomena. The need for a more comprehensive mathematical framework was palpable. Foley Thomas's work emerged in this very fertile ground, a time of intellectual ferment and rapid scientific advancement. His approach constituted a fundamental reimagining of how to grapple with complex quantities. He undertook a project to create a new language for mathematics, a language capable of describing and manipulating the intricate, often seemingly paradoxical, properties of complex numbers. This new mathematical language would prove essential for understanding and modeling a wide range of phenomena, from the behavior of light waves to the intricate dynamics of electrical circuits. The mathematical world at that time was largely confined to the realm of real numbers, while these numbers, representing quantities that could be directly measured and observed, were powerful tools for describing many physical phenomena. They were ultimately insufficient for capturing the full spectrum of reality. The very idea of a complex number, with its inherent interplay of real and imaginary components, was still a relatively novel concept, a source of both fascination and skepticism within the mathematical community. Foley Thomas's work was a monumental contribution to making these concepts more readily accessible and applicable. Foley Thomas's innovations were directly motivated by the pressing needs of the nascent wireless communication industry. The need to accurately predict and control the behavior of electromagnetic waves was paramount. His contributions addressed this critical need, providing a mathematical framework that would prove essential for the development of radio technology, laying the groundwork for the ubiquitous wireless communication we enjoy today. His mathematical approach was a pivotal step forward, embracing the full power and elegance of complex analysis. The significance of his contributions extended far beyond the realm of pure mathematics, influencing the very trajectory of scientific and engineering progress. The analysis of complex functions, a central theme in Foley Thomas's early work, would become a cornerstone of modern mathematical thought. The very act of defining and manipulating these functions, with their intricate geometries and subtle behaviors, would become a catalyst for profound insights into the nature of the universe. His innovative approaches to solving differential equations with complex solutions lay the foundation for future generations of mathematicians and scientists. His work was a direct response to the pressing needs of a rapidly evolving world, shaping the very tools used to understand and manipulate the forces that govern our universe. Foley Thomas's journey into the realm of complex analysis marked a pivotal moment in the evolution of mathematical thought. His early work, though often overlooked in favor of his later, more comprehensive contributions, laid the groundwork for the profound insights that would characterize modern complex analysis. This early exploration, driven by the pressing needs of his time, was a direct response to the limitations of existing methods and the burgeoning scientific questions that demanded new mathematical tools. The 19th century witnessed a growing appreciation for the power of complex numbers, yet their application remained largely confined to specific, relatively isolated domains. Existing methods for solving differential equations often faltered when confronted with complex solutions. This limitation was particularly acute in the burgeoning fields of wave phenomena and electromagnetism, where the behavior of waves and fields often exhibited complex characteristics. The need for a more comprehensive framework for handling these complexities spurred Foley Thomas's investigation. His unique insight lay in his innovative approach to defining and manipulating complex numbers. He recognized the inherent geometric significance of complex numbers rather than viewing them as mere extensions of real numbers. His work emphasized the intricate relationships between the real and imaginary components, highlighting the rich geometry embedded within the complex plane. This geometric perspective allowed him to develop novel techniques for integrating complex functions. Traditional methods, while valuable, often proved inadequate when dealing with the intricate contours and singularities that frequently arose in complex function analysis. Foley Thomas's approach was a fundamental shift in perspective. He recognized the importance of exploring the behavior of complex functions near singularities, points where the function's behavior becomes particularly erratic or undefined. His meticulous examination of these singularities provided crucial insights into the overall structure and properties of complex functions. This early investigation of singularities, though seemingly abstract, held profound implications for the study of wave phenomena. The understanding of singularities in complex functions directly influenced the development of methods for analyzing wave propagation in diverse physical systems, from light waves to sound waves and beyond. Furthermore, Foley Thomas's work on complex integration techniques proved remarkably effective in handling problems that were previously intractable. He developed new methods for evaluating integrals involving complex functions, allowing researchers to analyze a wider range of physical phenomena. These methods, involving contour integration and the application of Cauchy's theorem, served as practical tools for understanding wave propagation and electromagnetic phenomena. These techniques, refined and expanded upon by subsequent generations, remain essential components of modern complex analysis. Foley Thomas's early contributions to complex analysis retain significant modern relevance. His work, while rooted in the 19th century context, forms a cornerstone of modern mathematical thought. The principles he elucidated, the techniques he developed, and the concepts he introduced are now integral parts of university-level mathematics curricula worldwide. His innovative methods for integrating complex functions, for example, are still employed today in various fields, from fluid dynamics to quantum mechanics. The analysis of singularities in complex functions, a key focus of Foley Thomas's early work, continues to be a vital area of research. The interplay between singularities and the overall behavior of a function remains a central theme in complex analysis, with implications extending to diverse fields. His work also directly influenced the development of advanced techniques for solving differential equations, a critical component of scientific modeling across numerous disciplines. Foley Thomas's early explorations laid the foundation for a deeper understanding of the intricate mathematical structures underlying wave phenomena and electromagnetism. His insights into the behavior of complex functions, particularly near singularities, proved invaluable for analyzing these complex systems. His contributions to the development of robust integration techniques allowed for a more precise and nuanced understanding of integrals involving complex functions. The enduring impact of these early contributions is evident in the continued use of these techniques in modern scientific and engineering applications. His work, while centered on the fundamental principles of complex analysis, simultaneously addressed the pressing scientific questions of his era and profoundly influenced the trajectory of scientific progress. His early work, therefore, represents a powerful testament to mathematical innovation's enduring capacity to shape our understanding of the universe. Foley Thomas's contributions to the theory of differential equations represent a pivotal moment in the evolution of mathematical analysis. His work, deeply rooted in the challenges of his time, addressed pressing practical needs and simultaneously laid the groundwork for profound theoretical advancements. The era demanded robust methods for tackling nonlinear systems and the intricate interactions of multiple variables. Thomas's innovations, therefore, functioned as vital tools for understanding and modeling the world around him, demonstrating significant practical utility. The development of techniques for solving nonlinear differential equations presented a significant hurdle. Existing methods, often relying on linear approximations, proved inadequate for capturing the complex behaviors inherent in many physical systems. Thomas recognized this limitation and embarked on a quest for more general and accurate solutions. His meticulous explorations led to the development of novel iterative approaches, enabling the analysis of systems with multiple variables and nonlinear interactions. These iterative techniques, crucial for approximating solutions to complex equations, constituted revolutionary advancements, enabling the exploration of entirely new realms of mathematical analysis. Thomas's work encompassed a profound understanding of stability and instability, a pursuit integrated with his search for solutions. He recognized that the behavior of a system described by differential equation could exhibit dramatic shifts depending on the initial conditions and the parameters governing its evolution. His detailed analyses allowed for the identification of critical points and the determination of regions in the phase space where the system's behavior was predictable or chaotic. This insightful study of stability and instability represented a critical step towards understanding the dynamic nature of physical processes, laying the foundation for the study of chaos theory in later centuries. Thomas's exploration extended to specific types of differential equations, each demanding tailored solution strategies. He meticulously analyzed systems governed by partial differential equations, recognizing the unique challenges posed by these equations. His methods, refined through numerous examples, provided a framework for tackling equations describing wave propagation, heat transfer, and fluid dynamics. He crafted new methods tailored to the specific characteristics of each equation type. These specialized methods formed integrated elements within a broader theoretical framework, providing a unified approach to the analysis of diverse physical phenomena. The modern relevance of Foley Thomas's work on differential equations is undeniable. His methods, initially developed to address the scientific and engineering problems of his time, remain fundamental tools in contemporary mathematical physics. The solutions he developed are still employed in the study of numerous physical phenomena, from the intricate motions of celestial bodies to the behavior of electrical circuits. His work on stability and instability, for example, finds direct application in engineering design, where the stability of structures and systems is paramount. The enduring impact of his methods extends far beyond the confines of his era, shaping the very tools used to model and understand the universe today. Furthermore, the foundational concepts developed by Thomas played a crucial role in the development of more advanced mathematical tools. His work influenced subsequent generations of mathematicians, fostering a deeper understanding of the intricate relationships between differential equations and the physical world. His contributions were fundamental to the evolution of mathematical thought. The methods he developed constituted critical components in the broader evolution of mathematical analysis. The study of differential equations, a cornerstone of mathematical physics, owes a significant debt to Foley Thomas's pioneering work. His insights into nonlinear systems, his exploration of stability and instability, and his specialized solution techniques for diverse types of differential equations transformed the landscape of mathematical analysis. The techniques he developed, addressing the pressing challenges of his time, continue to be essential tools in modern scientific and engineering endeavors, proving the lasting impact of his groundbreaking contributions. The insights gained from his work constitute foundational elements that continue to shape our understanding of the universe. His methods provided a robust framework for understanding the complex systems that govern the natural world. Foley Thomas's contributions held significance for practical applications alongside abstract mathematical concepts. His work on Fourier analysis, a cornerstone of modern signal processing, addressed critical problems of his era, providing transformative solutions that continue to shape our technological landscape. The need for methods to decompose complex signals into simpler components was paramount. Imagine trying to understand the intricate sounds of a symphony or the intricate patterns within a complex biological signal. Dissecting these multifaceted phenomena into their constituent parts was crucial for understanding their underlying structure and behavior. The challenges were substantial. Analyzing periodic phenomena, those repeating patterns in time, required techniques that could capture the essence of these repeating structures. Existing methods often struggled with the complexity of these recurring signals, offering limited insight into their inner workings. Foley Thomas's innovative approach lay in the development of Fourier series and Fourier transforms. These tools, now fundamental to numerous fields, allowed for the representation of periodic functions as a sum of simplesine and cosine waves. This decomposition, a remarkable feat of mathematical ingenuity, opened avenues for analyzing complex waveforms in terms of their fundamental frequencies. He meticulously derived the precise mathematical formulations, establishing a framework for breaking down complex signals into their constituent components. The elegant simplicity of his solutions masked the intricate mathematical machinery beneath, demonstrating the power of abstract thought to unravel complicated phenomena. His work encompassed representing periodic functions and grappled with the critical issue of convergence. Understanding when and how these series accurately represented the original function was essential to their practical application. Foley Thomas meticulously explored the conditions under which these series converged, offering crucial insights into the limits of these analytical tools. His rigorous analysis provided a foundation for practical applications, ensuring the decomposition produced accurate results, preventing spurious or misleading outcomes. This rigorous focus on convergence held vital importance for the reliable application of Fourier analysis in diverse fields, serving purposes extending beyond academic exercise. The impact of this work reverberates through modern technologies. Signal processing, a field encompassing the manipulation and analysis of signals, relies heavily on Fourier analysis. From audio compression to image processing, the decomposition of signals into their constituent frequencies is the bedrock of numerous technologies. The intricate digital filters used in modern telecommunication systems, the sophisticated algorithms for medical imaging, and the powerful tools for data compression all owe a debt to Foley Thomas's foundational work. The ability to isolate specific frequencies within a signal, to filter out unwanted noise, or to reconstruct a signal from its component frequencies, or direct consequences of his profound insights. Consider the intricate world of medical imaging. Magnetic resonance imaging and computed tomography rely on Fourier analysis to reconstruct images from complex signals generated by the interaction of electromagnetic radiation with the body. The intricate patterns in these signals are translated into detailed anatomical images, enabling precise diagnosis and treatment planning. Likewise, the analysis of brain waves and other physiological signals relies on the same principles. The pervasive nature of Fourier analysis extends into realms beyond engineering and medicine. In the realm of music, Fourier analysis is applied to analyze sound waves, enabling the extraction of the fundamental frequencies contained within a musical piece. This method allows for a deeper understanding of the compositional elements. Similarly, in geophysics, Fourier techniques are used to analyze seismic waves, offering insights into the Earth's interior structure. The universality of Foley Thomas's methods underscores their enduring value. His methods possessed limitations, yet they provided a robust framework for understanding the complex systems that govern the natural world. The insights gained from his work constitute foundational elements that continue to shape our understanding of the universe. His contributions address the profound need for a systematic way to understand the intricate world of complex signals, transforming the landscape of mathematical analysis and laying the foundation for countless technological advancements. His meticulous attention to the convergence of these series proved critical for the reliable application of Fourier analysis in diverse fields. The legacy of Foley Thomas extends far beyond the confines of his era. His pioneering work on Fourier analysis continues to be a cornerstone of modern signal processing, medical imaging, and telecommunications. His insights into the decomposition of complex signals, the analysis of periodic phenomena, and the nuances of convergence remain essential to our understanding of the world around us. His work, a testament to the power of abstract mathematical thought, continues to inspire and guide researchers in diverse fields, proving the enduring impact of his groundbreaking contributions. His meticulous attention to detail and his profound understanding of mathematical principles continue to resonate with researchers today. Foley Thomas's contributions encompassed abstract mathematical theory and extended into the tangible world of practical application. His work, deeply rooted in the intricacies of Fourier analysis and the elegance of differential equations, offered potent tools for tackling the complex challenges of his time. The burgeoning fields of physics and engineering, grappling with phenomena like heat transfer, fluid flow, and electromagnetic interactions, desperately sought mathematical frameworks to understand and model these processes. Foley Thomas stepped forward, providing precisely the mathematical tools they needed. His profound understanding of complex analysis, a field he himself had significantly advanced, proved invaluable in tackling these problems. The intricacies of heat diffusion, the swirling complexities of fluid dynamics, and the subtle interplay of electromagnetic forces all yielded to his meticulous applications of differential equations. His work encompassed solving equations and translating abstract mathematical concepts into concrete descriptions of physical reality. Consider, for example, the challenge of modeling heat flow within a conducting material. This problem, fundamental to engineering design and thermal management, required a precise mathematical formulation. Foley Thomas, leveraging his mastery of partial differential equations, developed elegant solutions that accurately predicted temperature distributions within various geometries. His insights into the boundary conditions, the initial temperature profiles, and the material properties allowed engineers to optimize designs for maximum efficiency and minimal heat loss. His meticulous analysis provided engineers with practical blueprints for thermal design. Similarly, his work on fluid dynamics, by applying Fourier analysis and the concept of superposition to the Navier-Stokes equations, provided insights into the complex behavior of fluids, the interplay of forces, the formation of vortices, and the intricate dance of pressure variations within a fluid all became amenable to mathematical description. His work encompassed describing the behavior of fluids, predicting its future states, and controlling its dynamics. Furthermore, his contributions to the study of electromagnetism were equally profound. He applied Fourier analysis to understand the propagation of electromagnetic waves, laying the groundwork for the development of more efficient antenna designs and transmission lines. His mathematical tools, born from abstract principles, were directly applicable to the practical needs of telecommunications engineers, paving the way for faster and more reliable communication systems. One striking aspect of Foley Thomas's approach was his ability to connect seemingly disparate mathematical concepts. His application of complex analysis to problems in heat transfer, for example, revealed unexpected connections between seemingly unrelated phenomena. This ability to see connections, to bridge the gap between abstract mathematics and concrete physical realities, was key to his success. His work constituted a unified framework for understanding and manipulating these complex systems. His methods required an inventive spirit and a willingness to explore novel mathematical territory. He understood that the elegance of the mathematical solution resided in its capacity to illuminate the underlying physical principles, alongside its correctness. In essence, his work was a testament to the power of applied mathematics, demonstrating how abstract mathematical concepts could be translated into tangible solutions. The impact of Foley Thomas's work on modern engineering continues to resonate. His methods for solving partial differential equations are still taught in engineering schools worldwide. His applications of Fourier analysis to signal processing remain central to the design of modern communication systems. The mathematical tools he developed constitute active components of contemporary engineering practice. His insights into heat transfer continue to guide the design of efficient thermal systems, from the cooling systems in modern electronic devices to the insulation in buildings. His work on fluid dynamics shapes the design of aircraft, automobiles, and a myriad of other engineered systems. These enduring applications underscore the enduring relevance of his contributions. The legacy of Foley Thomas stands as a demonstration of applied mathematics at its finest. He showed how abstract mathematical ideas could be translated into concrete solutions, transforming the theoretical into the practical. His work is a testament to the profound power of mathematical thinking, a power that continues to shape our world today. The enduring power of Foley Thomas's mathematical and scientific contributions profoundly shaped the very methods by which mathematics and science were taught, disseminated, and advanced. The academic landscape of his era faced significant challenges. A growing body of complex knowledge required systematic presentation, researchers needed effective platforms to share discoveries, and aspiring scholars demanded rigorous yet accessible pathways into these demanding fields. Thomas recognized these needs and actively worked to build the infrastructure of intellectual progress. One of his most significant contributions to this infrastructure lay in the realm of mathematical education. He authored textbooks that became foundational texts for generations of students. These works were distinguished by their remarkable clarity and logical structure. They took intricate concepts, often previously confined to dense treatises or scattered papers, and presented them with a pedagogical precision that illuminated the underlying principles. The problems of the time included a fragmented curriculum and teaching methods that relied heavily on rote memorization or abstract theory disconnected from practical application. Thomas's texts addressed this by integrating theoretical exposition with carefully chosen examples and exercises that reinforced understanding and built problem-solving skills. Consider, for instance, the way his texts introduced new mathematical operations or theorems. They would typically begin with a clear statement of the concept, followed by an intuitive explanation that grounded in familiar ideas or geometric interpretations. This approach demystified subjects that many students found intimidating. He understood that true comprehension arose from seeing the connections between different mathematical ideas and appreciating their utility. His books encouraged an active engagement with the material, prompting students to think critically and apply what they learned, fostering a deeper intuition for the subject matter. Earlier teaching materials often presented mathematics as a collection of isolated facts and procedures. The organization of his textbook set a new standard. Complementing the excellent content, chapters flowed logically, building complexity incrementally. Definitions were precise, proofs were presented with meticulous detail, and the progression of topics allowed students to construct a robust understanding layer by layer. This systematic approach was revolutionary in its time, providing educators with a reliable framework for teaching and students with a clear path for learning. The widespread adoption of his textbooks speaks volumes about their effectiveness and their role in standardizing the curriculum in mathematics and related sciences across numerous institutions. They provided a common language and a shared foundation that facilitated collaboration and further study. Thomas also played a pivotal role in the development and strengthening of scientific research communities. Recognizing the importance of disseminating new findings and fostering dialogue among scholars, he was instrumental in the formation or revitalization of scientific societies and journals. These institutions served as vital conduits for the exchange of ideas, allowing researchers to share their discoveries, critique methodologies, and build upon each other's work. Researchers in his era contended with slow communication, difficulty accessing the latest findings, and the absence of formal mechanisms for peer review and validation. Thomas understood that scientific progress accelerated when ideas circulated freely and were subjected to rigorous scrutiny by a community of experts. His involvement in establishing or supporting journals provided a structured platform for publication, ensuring that important research reached a wider audience and contributed to the collective body of knowledge. He championed the principles of clear reporting, reproducibility of results, and intellectual honesty, helping to establish norms that underpin scientific integrity to this day. Furthermore, his participation in scientific societies facilitated crucial face-to-face interaction. Conferences and regular meetings allowed scholars from different institutions and even different countries to connect, present their work, and engage in discussions that sparked new ideas and collaborations. Thomas was often a leading voice in these forums, known for his insightful questions, constructive criticism, and ability to synthesize diverse perspectives. He fostered an environment of intellectual curiosity and mutual respect, encouraging younger researchers and bridging divides between different areas of scientific inquiry. The impact of Foley Thomas on his students and colleagues was profound and far-reaching. As a mentor, he instilled in them a deeper appreciation for rigor, clarity, and the pursuit of fundamental understanding. He challenged them to think independently, to question assumptions, and to push the boundaries of their knowledge. His teaching style was reportedly demanding and inspiring, encouraging students to strive for excellence and to develop their own unique intellectual voices. Many of his students went on to become prominent mathematicians and scientists in their own right, carrying forward his emphasis on foundational principles and rigorous methodology. He cultivated a collaborative spirit within his academic circles, fostering a spirit of shared endeavor, a valuable quality in academic pursuits. He was generous with his time and insights, always willing to discuss problems, offer suggestions, and share his expertise. He saw research progress as a collective endeavor, where shared knowledge and mutual support accelerated discovery. His colleagues valued his intellectual prowess, his integrity, and his collegial nature. He built strong relationships that facilitated interdisciplinary work and the cross-pollination of ideas between different fields. The educational methods and principles championed by Foley Thomas resonate strongly in contemporary academic practice. The emphasis on clear, structured presentation of complex material remains a cornerstone of effective teaching across all scientific disciplines. Modern textbooks and online educational resources continue to employ the pedagogical strategies he helped to refine, including starting with foundational concepts, building complexity gradually, integrating theory with practice through examples, and encouraging active problem solving. His approach to making advanced topics accessible while maintaining rigor serves as a timeless model for educators. the institutions and practices he helped solidify, specifically scientific journals with peer review, professional societies, fostering communication, and a culture of open discourse, form the bedrock of the modern research ecosystem. Technologies for communication have evolved dramatically. The fundamental principles of disseminating research, ensuring quality through peer evaluation, and fostering community through shared platforms trace a direct lineage to the structures Thomas helped build and strengthen. Moreover, the legacy of his mentorship persists in the value placed on graduate student training, post-doctoral guidance, and the cultivation of research teams. The idea that experienced scholars had a responsibility to nurture the next generation, imparting both knowledge and the values of scientific inquiry, was exemplified by Thomas. His influence lies on in the countless researchers who were shaped by his direct guidance or by the academic lineage that descended from him. His impact on education extended to promoting a broader understanding of the scientific method and the role of mathematics as a tool for understanding the world. He advocated for the importance of quantitative reasoning and logical thinking, skills he believed were essential for scientists and, indeed, for any educated individual. His work helped elevate the status of mathematics and science within the broader curriculum, arguing for their central role in developing critical thinking abilities. The problems Thomas addressed in education and research dissemination, the need for clarity, structure, and community, continue to be relevant today, albeit in new forms. The sheer volume of information available requires even more sophisticated methods of organization and evaluation. The need for effective communication of complex scientific ideas to both specialist and general audiences remains paramount. Thomas's solutions, rooted in clear presentation, rigorous methodology, and collaborative structures, provide enduring principles for navigating these modern challenges. His work reminds us that the advancement of knowledge depends on building the infrastructure for learning and sharing, alongside individual acts of discovery. Reflecting upon the principles Thomas championed in education and the dissemination of knowledge provides a vital lens through which to view the entirety of his intellectual legacy. His vision encompassed the very architecture of scientific progress itself, a scope extending far beyond the confines of individual research problems. The clarity, structure, and emphasis on community engagement that defined his pedagogical approach likewise characterized his foundational contributions across diverse scientific disciplines. He understood the groundbreaking discoveries gained their full power only when effectively communicated, rigorously validated by peers, and integrated into the collective understanding of a field. This holistic perspective, linking the solitary pursuit of truth with its communal diffusion, stands as a hallmark of his career. The enduring relevance of Thomas's insights into the infrastructure of knowledge mirrors the lasting impact of his theoretical and methodological innovations. His work furnished succeeding generations with powerful new conceptual tools and analytical frameworks. Consider, for instance, the profound influence of his formulations in areas previously marked by ambiguity or intractability. He provided the essential mathematical language required to describe phenomena with unprecedented precision. The specific structures he introduced, the elegant equations he derived, these elements became cornerstones upon which others could build. They offered solutions to the pressing challenges of his era. Their significance extended further, illuminating entirely new avenues of inquiry and revealing unforeseen connections between seemingly disparate domains of science. His contributions fostered a new level of rigor within his fields. The standards of proof he established, the meticulous attention to underlying assumptions, these elevated the practice of scientific investigation. He demonstrated how a deep understanding of fundamental principles, coupled with innovative mathematical techniques, could unlock complex problems that had long resisted solution. This commitment to rigor resonated deeply within the academic community, shaping expectations for future research and contributing to a culture of intellectual discipline that persists today. The methodologies he pioneered offered systematic approaches to problems, providing reliable pathways to verifiable results. The impact of Thomas's work extends into contemporary science and engineering, influencing the field directly and indirectly. Many of the analytical techniques he developed remain standard tools in various disciplines. His theoretical constructs continue to inform research at the cutting edge. His influence encompasses explicit applications. A deeper impact resides in the way he framed problems, the conceptual bridges he built between different areas of knowledge, and the emphasis he placed on the interconnectedness of scientific inquiry. He modeled an approach to scholarship that valued depth within a specialty alongside breadth across intellectual landscapes, a perspective increasingly vital in an era of complex, interdisciplinary challenges. Assessing Thomas's place in the history of science and mathematics requires acknowledging the multifaceted nature of his achievements. He was a creator of fundamental theory, a developer of practical methods, and a visionary educator. His work represents a pivotal moment in the evolution of thought within his fields, marking a transition towards greater formalization, increased analytical power, and a more integrated view of scientific knowledge. He did forge new paths in abstract thought and simultaneously provided the means for applying that thought to understand the physical world. His legacy is woven into the fabric of modern scientific practice, influencing how researchers formulate questions, how they seek answers, and how they share their findings. His innovation involved inventing entirely new conceptual machinery capable of addressing classes of problems previously beyond reach. He constructed new tools from foundational principles. This capacity for conceptual invention, coupled with a relentless pursuit of clarity and rigor, set him apart. He demonstrated that the most powerful advancements often arise from a willingness to question fundamental assumptions and to build theoretical structures from the ground up. The importance of his work stems from its dual impact, providing solutions to immediate scientific and engineering challenges while simultaneously laying the groundwork for future exploration. His contributions catalyzed progress across a range of disciplines, enabling breakthroughs that would have been impossible without his insights. He furnished the intellectual infrastructure necessary for subsequent generations to push the boundaries of knowledge even further. He solved significant problems. The methods he developed and the conceptual frameworks he established proved even more transformative, providing lasting intellectual capital. Thomas's career underscores the profound interconnectedness of research, methodology, and education. He recognized that the vitality of scientific progress depends on nurturing new talent and ensuring that knowledge flows freely and effectively throughout the intellectual community. His efforts to clarify complex ideas, to structure curricula logically, and to foster collaborative environments were integral to his overall project of advancing knowledge. He demonstrated that the cultivation of intellect through rigorous training and open communication is as essential to scientific progress as individual acts of genius. His perspective on the scientific enterprise offers valuable lessons for navigating the challenges of the present day. In an era characterized by exponential growth in information and increasing specialization, the need for clear communication, rigorous evaluation of evidence, and the capacity to connect insights across diverse fields remains paramount. Thomas's emphasis on foundational understanding and the development of robust analytical skills provides a powerful counterpoint to the superficiality that can sometimes accompany rapid technological change. His legacy encourages us to prioritize depth, clarity, and intellectual integrity in our pursuit of knowledge. The historical context surrounding Thomas's work highlights the intellectual landscape he navigated and the specific challenges he addressed. He entered fields grappling with certain limitations, facing problems that required new conceptual approaches. His genius lay in identifying these critical junctures and devising the precise theoretical and methodological innovations needed to move forward. He engaged with the scientific questions of his time with a unique blend of abstract reasoning and practical insight, a combination that proved remarkably effective. Reflecting on his life's work reveals a scholar deeply committed to the advancement of knowledge in its broadest sense. He viewed mathematics and science as fundamental tools for understanding the world and solving its most pressing problems. His influence encompassed the specific results he published, reciting powerfully in the intellectual habits he fostered, the standards he upheld, and the vision of a connected, rigorous, and openly communicative scientific community he championed. He stands as a figure whose contributions continue to shape our intellectual landscape, a testament to the enduring power of clarity, rigor, and a holistic approach to the pursuit of truth. His work remains a source of inspiration, reminding us of the profound impact a single individual can have in illuminating the complexities of the universe and in building the foundations for future discovery. The problems he engaged with, the solutions he crafted, and the intellectual legacy he left behind continue to resonate, guiding contemporary researchers and shaping the educational experiences of students worldwide. He carved a unique and indispensable place within the history of scientific thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.